Hello, my name is Scott Lowe, and I am the architecture lead on the Meridian Ground Systems team at AI Solutions. And today I'm here to talk about how we build flight dynamics ground systems using microservices that are built with Docker containers. If you have any questions at all about any of the content that I'm presenting, or really just want to have a conversation in more depth about this kind of technology, please feel free to send me an email. I'm always really excited to talk about any of this. But first, a little bit of a background on AI solutions. Since 1996, we've been focused on enabling mission success in the astrodynamics and engineering world. We've built a whole lot of flight dynamics ground systems. And to do that, we use FreeFlyer, which is our super robust astrodynamics and mission design tool. It's script based, so you can really do anything with it, and it makes it a super flexible solution for us to integrate with other pieces of flight system ground software. It really is the core piece of what we use when we're building a flight dynamics ground system. So let's take a look at how we typically set up flight dynamics for a mission's ground system. Generally, we start with a flight dynamics engine. In our case, we use FreeFlyer. We bundle FreeFlyer with a set of scripts and software, which together perform flight dynamics tasks required on a mission. And as the ground system continues to be developed, we add additional components and layers to handle all the various needs and capabilities of our target mission. What we end up with is a very custom tailored solution, which is great, but as requirements and capabilities are added, the resource needs of the support team increase with each addition. The system becomes nuanced, and you get to a point where you need dedicated subject matter experts just to understand how your system works. This is how things have been done for a long time, and it works, but it's not always scalable. For every new mission, you need to start from scratch and double your human resources. Two ground systems means two teams, right? You can't just copy your ground system from one mission to another in this approach. So, after doing this for years, we as a company decided to take a hard look at these components and figure out a way to create a generic solution. We wanted a way to develop a common set of scripts and software that any ground system could leverage to do the astrodynamics that are common across missions. We also wanted to bundle the infrastructure that goes into building a flight dynamic system and reduce or eliminate common time consuming system administration tasks. The solution that we came up with was Meridian. This is what we call flight dynamics in a box, taking a holistic look at building the flight dynamics ecosystem and packaging it into something that can be repeatable. And turns out, this makes it easy to maintain across different missions with different requirements. Just like a car, we build a common reproducible frame around our engine. We bundle a customizable set of microservice components that are common to a ground system with our flight dynamics engine. By allowing each mission to choose only the microservices they need, we create a flexible system that can maintain a common standard, but can also be custom tailored to mission requirements rather than reinventing the wheel each time. This approach also scales really well, which becomes increasingly important as we support more and more constellations. And overall, this eases development, installation, security, maintenance and upgrades, and customer support. I mean, as you can imagine, having a single system that is well understood by a support team means you don't need a dedicated support team to solve every single mission event that comes up. But taking all that and packaging it neatly is way easier said than done. A ground system consists of so many components, and this can be an overwhelming task to try to package them all. So, how do we develop a standard packaging structure for our microservices in a way that reduces the work to the system administration team rather than add to it? Well, we do that with a technology known as containers. So, what is this esoteric technology all about? What is it, and how does it solve the problem? Well, in a nutshell, containers are just a way of grouping a process or a piece of software and its environment together. Usually, this is a single process, like a server application, along with its configuration, environment, and network settings. This gives us a standard way to create microservices that are completely encapsulated. It makes system administration simple. A microservice in a container can be installed in any environment with little to no setup because the container includes everything that the microservice needs. In a way, this is like wrapping each service or application with its own lightweight operating system, but not the whole operating system. In the industry, this is what's called OS level virtualization. Each container has its own tailored set of dependencies, such as specific versions of things like programming language runtimes and libraries. It also includes its own file storage and network settings. And in this approach, you can instantiate or clone multiple instances of your microservice and guarantee that each instance of the microservice has its very own ecosystem to work with that's independent of anything else on the operating system. So, for instance, say you wanted to run orbit propagation or maneuver planning for each and every spacecraft in a constellation of 1,000. You could instantiate 1,000 identical copies of an orbit propagation container without having to do any system configuration. So each container has everything it needs to run its task against the set of input data. So, how does all this really work? Well, to get a better idea, let's take a step back and look at how we've traditionally set up a computer in a ground station server room. Well, normally we'd start by purchasing the server hardware, a single computer and a server rack. We'd install an operating system on that server, and we configure that server's operating system in a specific way to meet the mission's needs. And 10 years ago, this was pretty much the common way. Have a separate physical server running a single operating system, custom tailored with its own applications and settings for a specific purpose. More recently, server rooms have increasingly become virtualized. In this approach, you have one large server rack with a large set of physical hardware built to support the entire server room. And this hardware is installed with a hypervisor, which is an operating system designed to support multiple virtual machines. In this setup, a system admin can create as many virtual machines as they need, each with its own operating system, application, and settings. And they can create a new virtual machine simply by running a few commands. This is a fantastic approach in many ways, but it's still somewhat monolithic. An admin is still creating and copying entire operating systems. They're still managing things like system dependencies on each operating system, and this can be costly in terms of time and resources. Enter containers. Containers are like virtual machines, but much more lightweight. Whereas a virtual machine splits up the physical hardware into virtualized machines, containers split up the operating system kernel into virtualized operating systems, or more technically speaking, virtual user spaces. Containers typically only contain a single application, which means instantiating a container takes up significantly less overall system resources than instantiating a new virtual machine. They are configured and managed by a system service, or daemon, known as a container engine. The container engine is way less intrusive than a fully blown hypervisor, and altogether the container ecosystem requires significantly less resource overhead. On Meridian, the container engine we use is called Docker. Docker allows us to create a flight dynamics ground system that has a single dependency. As long as the Docker engine is installed on our server, our containers can be deployed in minutes and instantiated in seconds. We'll get to the difference between deployment and instantiation in a short bit, but before that, let's talk a little bit more about how Docker fits into the container world. Docker is one of many in a sea of options. The ecosystem of container engines on the market is vast, and covering all the options would take several days worth of presentation time to cover. Right now, Docker is the front runner, but it may not stay that way forever. But for now, Docker is by far the most popular, and it's what we use on Meridian. And it does an incredible job of making containers easy. One of its greatest features is its cross-platform compatibility. It bridges the gap on operating systems and allows us to run containers on Linux, Windows, or Mac. On Linux, it works using Linux's native namespacing capability. On Windows, it uses Windows' built-in hypervisor, Hyper-V, to create a container kernel. On Mac systems, Docker comes bundled with its own hypervisor. Docker makes it so that despite the differences behind the scenes, a container is run in the same way regardless of the underlying operating system. This means we can test what we fly and fly what we test. So, throughout the use of Docker, we are able to create microservice containers and achieve our goal of building a flight dynamics ground system in a box. By deploying our components as container microservices, we are able to build our software to be task specific without having to worry about the overall ecosystem. The ground system servers can be configured in any way, and we can guarantee that regardless of configuration, our containers will still be compatible. Each mission can be customized by selecting only the containers necessary to meet their specific mission requirements. But how are containers deployed? Well, traditionally, ground station software installation and maintenance are really projects in themselves. To illustrate an example, let's compare a traditional software deployment with one that's Docker based. Typically, a deployment goes like this. Take a bunch of production files generated in a development environment, things like compiled code, software, configuration files, etc., and copy them onto a production machine. Many software packages offer installers, but in ground system development, this isn't always the case. And even then, each installer has a different process to follow. There's lots of different checklists, and a system administrator really has a lot to do to get the system up and working correctly. And as anyone who's ever done this can tell you, deploying on servers is problem after problem after problem. And even after things are successfully running, maintenance and upgrades are usually problematic, or at least very costly. There's a whole lot of bean counting, checklists, configuration management, and approvals to go through, all to keep that software emission safe. I'll admit, when I was a young engineer just breaking into aerospace, I was pretty surprised to see some of the maintenance procedures involved. You can use things like version control to manage the differences, but this can still get complicated quick. It's always a nightmare for your system admin. Frankly, it's why they get a whole day of appreciation each year. Developers sometimes forget to tell the system admins which versions of software were updated in their latest release. Human error can creep into configuration management checklists, and even installation scripts can go wrong, and do. So let's see what adding Docker to this equation looks like. With Docker, we can organize all of our mission critical processes and required environment settings into containers. We can run our development environment on Windows, even if our operational environment is running on Linux. By using containers as a standard, we can make components generic and design the process independent of the operational environment. And so deploying with Docker becomes as simple as bringing the container over from our development environment into our operational environment. Again, it doesn't matter what the operational system looks like as long as it's got Docker on it. So hopefully that illustrates how useful containers can be in deployment. It's how we've been able to achieve installations that take as little as 10 minutes for an entire Flight Dynamics ground system. But like I said before, installation is a little different than instantiation. Installing containers is one piece of the process. Just like any piece of software, a container that's been installed on a system doesn't necessarily mean it's running. Running a container can be very simple, but especially in cases where we'd like to run thousands of containers, it's really important to know the tools involved in managing the container ecosystem. To do that, let's take a look at a simplified list of tools we have at our disposal. This is by no means a full list of Docker terms, but these are the most common pieces we use in our ground system development every single day. So first off, there's the Docker daemon. This is the background service that's really doing the work, the beating heart of Docker. Although there's more that goes into the Docker engine, you can think of the daemon as the engine throughout the rest of this presentation. Now there's a couple ways we can interact with the daemon. The Windows Docker has a nice friendly user interface, for instance, but the most important way is through the Docker CLI, which gives you commands that you can use to control the running Docker daemon. And then there's the registry, which is an external way to store and manage containers. The daemon keeps track of containers locally, but the registry allows you to track available containers securely over a network. Now the terms listed here under Docker objects are important to the lifecycle of containers. And there's really three primary phases to a container's lifecycle. Creation, which is done through the use of a Docker file. Container management. In Docker, containers are stored as Docker images. And a running instance. And remember, a container is a running process which is bundled with its environment. So let's take a look at how all these things work together. A typical lifecycle looks something like this. We use a Docker file to build Docker images, and then the images in turn are used to instantiate running containers. In this example, a developer takes a Docker file, which is like a recipe for creating an image, and then calls the Docker build command on the CLI. When our developer runs the Docker build command, they are using the CLI to tell the Docker daemon to create an image. The doc argument after our Docker build command tells Docker to look in the current directory for the Docker file and any other files in the current directory that the Docker file needs to create a container. And the T argument is how we name our container image. The CLI reaches out to the Docker engine, which uses the Docker file and local system files to generate an image. Once the image is generated, it exists locally in our Docker engine, which keeps a collection of all the images that have been created. We can, for example, view this list of images with the docker image ls command. It's important to note that when an image is generated, it's tagged and hashed, which guarantees the identity of its content. And we can use this for things like configuration management. Before we jump into instantiating a container though, let's look at the options for maintaining and deploying our images. So as we know, the Docker engine itself keeps a collection of images, but the Docker ecosystem also has this Docker registry. The Docker registry is really simply a network-enabled repository for Docker images. It is optional. In no way is this a required part of the Docker ecosystem. A popular example of a registry is Docker Hub, which hosts container images publicly. Of course, registries don't need to be public and are often hosted within a private secure infrastructure. But either way, images can be pushed and pulled to and from the registry, and this is often the preferred choice for container development and deployment in the public world. However, we all know that ground systems are usually built on air-gapped secure networks. So in the case where the development environment is not on the same network, or a Docker registry isn't available, we can also save our Docker images locally as a simple tar file. The image can then be delivered via secure FTP or USB, or any system that transports files. In operations, a Docker engine can be populated simply by running the docker load command on the CLI. This mechanism also allows for images to be named with a tag or version number so that different versions of a container can be maintained on both systems. Alright, so once we've delivered these images, instantiating a container is really as simple as running the docker run command followed by the name of the image. The command uses the Docker CLI to tell the Docker daemon to use the specified image to create an instance of the container, regardless of how many instances of the container are already running. The container will then run indefinitely in the case that the container is built as a server application, or it'll run to completion. The Docker PS command will list all running containers, just like the Docker image ls command in a previous part of this presentation listed all of the available images within the Docker engine. So there are a ton of ways to run containers, but that's also another topic worthy of many other presentations. But for now, with the life cycle of containers fresh in our heads, let's use Meridian as an example of how we build a real flight dynamics ground system. So you'll remember that we historically start with our flight dynamics engine, and we package it with a set of scripts that supports common mission operations. So as part of Meridian, we created an API to extend that engine, to develop a standard that other parts of the ground system can use to interact with the engine. But what else do we typically need in a ground system? Well, a web interface that allows operators to have control of our system would be nice. And in between, we know that we're going to need an automation service to run regular tasks like daily or weekly product generation, a REST API to coordinate access between our components, and a database for persistent mission storage. And of course, we'll need system admin access to perform maintenance and upgrades, and connections to multiple external systems to do things like ingest telemetry and deliver products. And as we develop our system, we find ourselves in a familiar situation. When we built Meridian, we knew that the organization and management of all these in-betweens was going to be a challenge. So we made the decision right from the start to use Docker. And we know now that by bundling each of our server components into its own container with its own ecosystem, that we can install a large variety of applications and only require the installation of a single dependency in our operational system. This is great for all the reasons that we've talked about, but how do we get everything working together? We've explored how bundling processes with environment cleans things up, but it's not enough to have these containers running in isolation. Our components need to be sharing files and data, and we still have to keep our components connected to the network. So to do that, we're going to take a look at one more tool in the Docker ecosystem, and that's Docker Compose. So while Docker has Docker Engine to handle the running of individual containers, Docker relies on Docker Compose to handle the orchestration of container collections. Docker Compose gives us the ability to configure the in-between and define rules for how different containers interact with each other, the host system, and external hosts on the network. It allows each mission to be configured with only the containers necessary to support the mission tasks and requirements. So, how does it do all this? Well, here's an example Docker Compose file. Each container is defined as a top-level node that you can see here. In this example, we have a web interface, a REST API, and a database from our ground system. Each container references the specific image that it should use to instantiate. Each container defines the ports that are available and how they map to the network defined on the host system, as well as external hosts. We can map environment variables between the host and the container environment, and even custom define variables for the container. Finally, we can define a dependency tree where we can tell some containers to wait on others before starting up. The command on the right is how we turn on all of the containers defined in the compose file. So let's see this working for real. Here we see a real example of the Docker Compose up command, which uses a Docker Compose file to tell the system how to start up. Now we go to the URL and we see the login page. This shows us that the web interface container network is correctly mapped to the host network and enabling it to serve the web contents. As we log in and take a look at the products in our system, we know that the REST API container is correctly mapped and able to accept connections from our user's computer, and that it's working correctly with our database container. And as we run our orbit propagation task, we see that our REST container is successfully passing our data to our FreeFlyer API. So, that's a top-level view of how we build a flight dynamics ground system using microservices and Docker containers. I hope this has helped illuminate some of this container technology and showed a little bit more about how we could leverage this technology to create a clean and scalable ground system. please feel free to reach out and contact me again if you have any questions or, again, just want to have a conversation. I'm always very excited to talk about this. Thank you very much.